video, I'm going to be explaining another important article about domain adaptation, but this time the measure of domain shift and those things is not domain maximum mean discrepancy. We are not using adversarial approach. We are just using Wasserstein distance, just like the previous video. So this paper in 2022. We studied the label shift problem between the source and target domains in general domain adaptation settings. We considered transformations transporting the target to source domains, which enable us to align the source and target examples. Through those transformations, we define the label shift between the two domains via optimal transport and develop theory to investigate the properties of domain adaptation under various domain adaptation settings. Because in the literature we have something closed set, we have partial set domain adaptation, we have open set domain adaptation, we have universal domain adaptation, and many other things. Inspired from the developed theory, we propose label and data shift reduction via optimal transport, which can mitigate the data and label shift simultaneously. Finally, we conduct comprehensive experiments to verify our theoretical findings and compare with state-of-the-art baselines. For example, label shift, you can have more kind of cats in test set than in the training set. Another example of label shift, which is different from my previous slide, is that training on data with few sick patients, test on data during flu that the probability of flu is greater, but flu symptoms are still the same. Or in speech recognition that train on the newscast data before election, test the newscast after election. For domain adaptation, the source domain consists of data distribution with the density P sub S and the unknown ground truth labeling function, assigning label to source data, while these are P and F for a target domain respectively. While the data shift can be characterized as a divergence between P sub and P sub T, the label shift in these works is commonly characterized as this expectation over target and this expectation over source, in which the binary classification with deterministic labeling was examined. Additionally, although this label shift term has occurred in the theoretical analysis, it is restricted in considering the shift between S and T at the same data, which ignores the data shift between source and target probability. This limitation is illustrated in figure 1, but the contributions are two in this paper. First, they characterize the label shift for a general domain adaptation setting via optimal transport. So from that, they develop a theory to estimate the label shift for various domain adaptation settings and study trade-off of learning domain invariant representations and Wasserstein label shift. Second contribution is that, inspired from the theoretical development, they propose label and data shift reduction, which aims to mitigate both data and label shift. So this is an illustration of label shift definition. The white or square points correspond to white square points on the target domain. So from the source domain to target, you see that they measure they define the label shift with respect to L as this expectation. And finally, they take infimum over all valid L to define the label shift between two domains. So what is the label for the source? What is the label for the target? And what is the difference? So for a positive integer, n indicates the set, and everything, the notation is standard, but here we see that they examine the general supervised learning, consider hypothesis H in a hypothesis class, big H, and a labeling function. So this F we are talking about is labeling function. And we further define a general loss of the hypothesis H with respect to the labeling function. So we examine various domain adaptation settings based on the labels of the source and target. For example, in the closed set, we know that there are labels matches. In the open set, YS is a subset of Y of target. In partial, Y target, this could be partial, and we have universal. But due to occurrence of data shift, it is challenging to formulate label shift in a general domain adaptation setting. So we addressed the issues by defining a novel label shift problem framework using this Wasserstein distance for general domain adaptation. So we have this label mismatch between source and target. So we say that there exists a transformation L from your target to the source. I've explained this push forward in this reference in maybe previous video. Given that mapping L, a data example with the ground truth prediction probability corresponds to another data example. Because here L, we have a mapping from target to source, so here is the source. But here is the label of target, and here is the label of source. So with this mapping, we are able to, to see the difference between them. Now, d sub y here is a given metric. The label shift between the source and target domains can be written as this expectation. Because it's not just based on just two samples, so the expectation overall samples on the target. And for each of them, we map to the source and then the difference between their label shifts, and then get the expectation of all of these. Now you should know that what is the label shift between T and S. The label shift between source and target is defined as infimum. So this infimum of the label induced by all valid transformations, because it's not just one fixed transformation L that we discussed here from target to source, we are talking about all transformations. So we take the infima. And then there are some properties of label shift that we can talk about using Wasserstein distance. We can prove that the label shift between them is just the Wasserstein distance between the source and the target. I think we proved this, we showed this in the previous paper, in the previous video, that all of these things, including this upper bound on the loss of the edge target FT and PT, which is upper bounded by label shift between S source and T, and Wasserstein distance between the probability distributions. Minimizing data shift while ignoring label shift can hurt the prediction on test set. So we define a new metric, D sub Z, with respect to the family of hypotheses. And you know that, like previous two videos, Z1, Z2, they lie in the latent space. So we have this upper bound on the label shift. So the good thing about this framework is that they can use it, they can understand partial set setting, different kinds of problems like open set domain adaptation. For all of them, you have this lower bound. So you see the factors that are essential in this label shift. So we train the source classifier on the label source data by minimizing the loss. And then another loss is shifting loss, that we mitigate both label and data shift. We propose to further regularize the loss. And the third one that we didn't talk is clustering loss, to enhance the smoothness of your transformation. Your classifier, for example. We enforce the clustering assumption to enable H sub T giving the same prediction for source and target examples on the same cluster. To employ the clustering assumption, we use virtual adversarial training in conjunction with minimizing entropy of prediction. So this is the entropy loss, and this is the virtual adversarial training, which is the expectation of the maximum of the KL divergence between the HT of G of X and X prime. So as I said, we just have three losses: clustering loss, shifting loss, and the standard loss that we know. The standard loss is just the source classifier.